Welcome to Breadboarding. This is video 24 in the Breadboard 8088 PC series, looking at PC Compatibility Part 2, where we'll be installing the new breadboards that we created in the last video and configuring a BIOS. So this was the board as we left it in the last video. So we've hooked up most of the components there. We just need to wire in the data bus, some of the address bus signals and control bus signals reset and things like that. Before we do that, this is our what makes a micro IBM PC compatible. So we've done a number of the items on here already in the previous video. Now we're going to configure the BIOS compatible with IBM PC software interrupts. And this is the overall plan. So these are the steps we're working towards booting MS-DOS from floppy disk in this phase of the project. We'll be looking in the future phase to build out real-time clock, disk controller, color video controller, and eventually try and run up an early version of Windows. So in order to get the BIOS running, first of all, I did forget in the previous video to review the PLD configuration for the system Clock PLD and the IO decoder. So I'll have a look at the schematic and review those PLD configurations in a minute. Then I'm going to install the Clock PLD onto the CPU clock board. We're going to check that the computer's still working after installing that we can actually see the video signals and we can get the monitor prompt coming up. Then we're going to wire in the board that I showed on the earlier page. To start with, we'll just test the speaker circuit with a signal generator output just to make sure that the speaker part is working. We'll also put a logic analyzer on the power on self-test port and we'll test out to see whether or not that works before we actually start to do the BIOS. Then we're going to download and configure Sergei Kiselev's 8088 BIOS. Now, to go through the BIOS in detail is going to take quite a while, and I suspect I might just try and get this working first of all, and we'll go through the BIOS in some detail, perhaps in another video. And then all we're going to do is to download the BIOS, and we can relocate the code segment to 6000 using the E command that we added to the monitor. And then we should just have to type go FFF0. And what we should then see, hopefully, will be the startup messages and some beeps, hopefully, if all's going well. So before we plug in a new board, I've changed things around a little bit. So this is the Clock PLD that was over here. And what I decided to do is to move this actually closer to where the CPU is. So there's the power supervised circuit here. We've got the 8284 clock generator chip here. And what I'm going to do is shuffle things around so we can fit this PLD in here. And what this is going to do is take the peripheral clock, which is 2.4 megahertz approximately. It'll also take the CPU clock, 4.77 megahertz, and out of there it's going to generate the appropriate signal for the DMA clock from the Clock 88. This has closer to 50% duty cycle, and then the programmable interrupt clock needs to be half of P clocks, about 1.19 megahertz, and also using this to produce the inverted reset signal as well. So we're just going to look at the board to see how to fit that. So you can see here's the PLD, and in fact I think we will be putting it in actually the other way around, so these pins will be facing over there. What we're going to do is to take out the reset button there, because we have got a reset button on our keypad anyway. So we're going to move this little lot up here, we're going to move this lot down a bit, and then hopefully there'll be sufficient space for this to then fit in somewhere around there. We'll also just take a look at the PLD configuration. Okay, so this is a system clock PLD configuration. It's using an ATF16V8, so this is the smaller of the chips. This one's a little more tricky to get working with the clock and the flip-flops. What we've got here is the peripheral clock is the input clock, C88 is the Intel 8088 CPU clock, and this has got the 3367 duty cycle reset, and then out of this DMA clock is actually produced by merging a number of these delayed clock signals. So we've got our various signals here, and basically the inverted clock, when the reset is active, then we're stopping the clocks and things from running. There were some problems I had with this PLD when I was first trying to do it before I introduced the reset clock, and it was getting itself confused at power on, and if the clock was running when it first switched on, then it was causing all sorts of problems. So by incorporating the reset in here, then hopefully that has resolve those issues. And you can see down here that the programmable interval timer, or the timer chip, has its D input to the flip-flop is just the inverted output. So this basically toggles the value backwards and forwards with the clock. So basically halves the frequency of the input clock, which is the 2.4 megahertz peripheral clock. And you can see here that the DMA clock is in fact a combination of this clock 5 signal and the initial inverted clock combined with a reset. And basically this is a NAND, and it basically what it means is that we're just relying on the 10 or 15 nanosecond delay through these various gates here, and overall this will actually result in the duty cycle actually becoming closer to what we need it to be. So I've already burnt this into the PLD, and similarly I realized I hadn't covered this one in the previous video. So this is the IO port decoder. So this takes in all the address lines A0 all the way up to A11. We also make use of this signal that we had previously, which basically goes low when A19 to A12 are all low and one of the IO read or IO write arrays. Then these are all our chip select, chip enable signals. And then these logic conditions down the bottom here are relatively straightforward. They're just combining the various address line values to give these IO ports that we had in our spreadsheet over here. So this is the spreadsheet where we defined all of these in the previous video. So now I'm going to move these chips around so I can remove the button and do the other things we talked about. So what I'll do is I'll speed that up and commentate over it. When we come back, hopefully this will be working. I'll try just powering on the computer to see that I haven't broken anything in the meantime before we start adding all the other bits to the system. Take out the reset switch, move up the power supervisor a bit, wire in the power and the reset button. Just need to get the tolerance to be pulled to 5 volts there. Pull up resistors and the LED to show when the processor is running. That's the strobe input which goes to the peripheral clock. In fact, I did wire in that second blue line should go into the low reset, not the high reset. So that's one of the things I had to fix. It's now just moving these other wires down for the 8284 clock controller. Again, I put the resistor there, should be going between X1 and X2. It's actually one hole down. So those are the two mistakes I made in doing this bit. So the pull-up resistors and that tied to ground. Now just put in the PLD, wire in the power rails, put in the decoupling capacitor. So output enable needs to be tied low. Putting in the P clock and the P clock going up to the strobe for the power supervisor. And this is the reset line coming down, but this is one hole too low for the moment. It should be on the low reset. Then wiring in the clock going down to the CPU. The reset and the ready signal from that controller, just checking all those leads that are going off down to the CPU, and that's the reset output. And wire in the 88 clock. So I finished installing the Clock PLD here, moved everything around. I made one or two minor mistakes. The resistor wasn't quite in the right place and the reset line was going to the wrong output of the power supervisor reset circuit up here, and so it was permanently in reset, and so I had to do a few fixes there. And we're just going to power this on now, so we should see our Nanocomp monitor display here. Yep, so we're getting Nanocomp 8088 version 3 coming up there. What I am just going to do is to put this into load, and we're going to download one of the test programs, and we'll just check to see that the video card is working. So I'm just downloading one of the test programs. We're going to type go, and then I will switch over to the capture card. Okay, so this is now the video capture card, and we just run that. Okay, so that appears to be working. So the video output, this is in its sort of monochrome green mode. rather than the color mode. So that all seems to be working. So I think we're in good shape to now add the other card into the circuit and then start to actually look at doing the BIOS. We're just going to look at a few of the clock signals whilst things are running. So this is the Clock 88 input. So this is the 4.77 megahertz. On the actual LCD display, it's showing as about 36-37% duty cycle. So this is the DMA clock, and we can now see that this is a lot more symmetrical. And in fact, on the display here, it says it's about a 50% duty cycle. So we've basically been able to change the duty cycle by a few of the gates in that PLD, so that looks to be good. So when we come to the DMA in the future videos, then we've now got the right clock for it. And now if you just have a look at the programmable interface timer clock, again this is now showing at 1.19 megahertz. So that is the frequency that we need to drive into the timer. Okay, so I'm ready to plug the new board in. So you can see up here, I've added a power connector on the top right up here, which is connected to the power connector just off camera there. Where we've got the various sort of flying leads here, this is where we need to plug in other cables down the bottom. So we just need to plug this board into the end here. Should just clip over the end. Okay. And now what I'm going to do is to wire up the interrupt acknowledge, the interrupt lines. There's the A0 and A1 reset, IO read, IO write need to go over there, and then there's the various address lines and things that need to go to there and around here. So once we've done all that, then we'll come back and then hopefully be ready to power on. Okay, so I'm just going to put the red lines are interrupt related lines. So that's the interrupt request. And then this one is the interrupt acknowledge, which comes from the bus controller. Just put that back in up there. Now we're putting in the IO read and the IO write, which go all the way down to the IO lines, bus lines, which are right at the bottom of the board there. Put in the reset. Just check those off. So now I need to put in the A0 and A1 down the bottom there. Now I'm just going to wire the rest of them up using the DuPont cables there and the data bus as well. Okay, so this is now all plugged in, and I've got the logic analyzer out because we're going to just test the speaker first. So we've reviewed our system clock and IO decoder PLD configuration. We've installed the Clock PLD on the CPU board. We've connected the new boards all the way up to the rest of the micro. Now I'm going to test the speaker circuit with the test oscillator. So 400 Hertz is, I think, is the frequency that the BIOS uses for some of the beeps. And we're also going to monitor the power on self-test port. And I've got a simple program that just writes sequential bytes to the port just so we can check to see whether things are working okay. So here's a logic analyzer, and it does have two pulse generators here. So all I'm going to do is to unplug. This is the output of the speaker. All I'm going to do is to plug in the ground and the output of the signal generator. So that's going to the driving the transistor there. Now we're just going to check the frequency on the logic analyzer. So we have in the PWM settings, that's 400 Hertz. So that should be driving that. And if we just switch the power on, if we hear a tone, then that should indicate that everything's working there. Okay, hopefully you should be able to hear that tone. Okay, so I've hooked up the logic analyzer to the power on self-test port. I've wired the speaker back in over here, removed the signal generator out of there. I've got a test program which I'll just quickly show you. So this is based on one of the MDA video controller tests with the attributes color, no blink. But I've added a post part of this. So if we have a look here, you can see here that we start with FF, a little bit of a delay, and then we move the counter into AL, output AL, to port 80, which is the post port, then loop back round. So that will go from FF down to 1, I think this should do. So I'm just going to switch on the nanocomp. Just going to send that down to the nanocomp. Okay, and then we'll just record perhaps 20,000 sample, 200,000 samples. And this will just wait for the post chip select to go low, and then we'll run it. There we go. So we seem to have some output there. So if we have a look on the right hand side here, we can see that we've got FF going all the way down to FE. If we go all the way down, you can see that we should be going down towards 0, 1. There we go, it goes down to 1. So if we just zoom out, we can see here that the thing is cycling and we're actually getting all of the post output, and we can also see here the post chip select is going low there. That appears to be working okay. So now I've tested the speaker and the post port, so we know we're getting some output there. So what I've now done is downloaded and configured Sergei Kislov's 8088 BIOS, so the URL is there and I'll include it in the description below the video. And I'm not going to go through the details of that now, I'll probably leave that for another video, but just to show you what I've got here, I've got the BIOS where I've configured it for the Breadboard PC. I have the default here, so I can do a WinMerge to show the differences. I've made some modifications here according to the slide here. So I've created a Breadboard PC configuration. I've configured various options. I'm going to relocate the BIOS code segment to 68000. So what I'm actually doing is changing the code segment and the extra segment to 6000 when I actually load the srecord file, and when I run it I also set the code segment to 6000. So this should mean that the code can coexist with everything else. Because the default BIOS will go through and test all the RAM, then I need to set the max RAM to just 256k so it doesn't overwrite the RAM where we're putting the BIOS. And this also includes the changes to initialize the 6845 registers and the video palette as well, if it gets that far. So the command to make this, I've modified this so it actually builds the configuration I'm interested in. So we just run make. I'll go into all the instructions on how to do this another point in time. And then if we just have a look at the output files that we've created. So this has created the binary file, which is about 32k by default. We've got an srecord file and we've got the list file, which is showing the output of the assembly process. So I've restarted an nanocomp. What I'm going to do first of all is type E6000. So this changes the extra segment to 60000, and this means that the load will actually load the downloaded file into that area of memory. And so if I now just go back and I'm going to send that srecord file. So this is the BIOS Breadboard PC 8088. I'll just send that. It's actually quite a long file. It's about 77k, so it takes a few seconds for that to download. So you can see here it's finished. So what I need to do now is to set the code segment to 6000. So this means now when I type in go, then this should theoretically run everything in the area where I've just loaded. So I'm going to execute the BIOS from FFF0, and that's going to be effectively 6FFF0. So let's just have a look here. So we can see here, yep, so we've set our code segment to 6000, and we're going to do go FFF0, and we're just going to go now to the post information here. So we've got our previous post information here, and if I just run this now, this should capture any post information. I'm not expecting it to get very far, but I would expect to at least get to see a couple of post codes. So now we're just going to type in the extra 0 to get it to execute, and that has run. Excellent, so it has done something. We've got it doing 01, 02, 03 and 04, so it hasn't got any further than that. And what we can do is to look up in the BIOS files, there is in fact the error number. And so what this shows is what the various error numbers are. So CPU test, initial chipset configuration, initialize the DMA, test the low RAM, Then it goes on to test the interrupt table and initialize the timer. I suspect that at the moment it hasn't been able to initialize the DMA because we haven't added the DMA yet. But we do seem to be getting some outputs here. We haven't quite got far enough to start the timer and to actually get speaker output, but it's looking like we have actually got something running there. I'm going to take that as a good start. I need to go into this and actually see if I can comment out some of the bits that might be preventing this. And then when we come back to the next video, what I will do then is to go through the BIOS configuration in more detail so that we can actually understand what all the configuration settings are and what all the different steps that we need. But it looks like we have actually got the BIOS to load. We've got a couple of postcodes, but we haven't quite got far enough to get the beeps working yet. But hopefully in the next video, we'll be able to perhaps comment out the DMA controller initialization and get the timer to initialize. So if you don't want to miss out on future videos, please hit subscribe. And if you could hit like, it just helps to make the videos available to a wider number of people. Thanks for watching.